Good morning to one and all. Morning. So you please kindly confirm audio video on screen. Is it okay for all? Please kindly confirm the audio video on screen. Okay. Right. So till yesterday we have discussed about the classification of lines and equivalent circuits of each and every line that we have seen. So now I am going to take up a different discussion here. Just go through it what I am saying you. Listen to this. For example, okay, we have one three-phase transmission line. Maybe I can say flat spacing three-phase line, and it is transposed, of course, right? So like this, we have phase A conductor, phase B conductor, something here, and then we have a phase C conductor. Listen to me first. Listen to me. So these are ABC conductors we have, three-phase system. Distances between the conductors might be given some numbers, whatever it is. Radius of each and every conductor also mentioned for you. Radius of each and every conductor is given, as well as distance between the conductors is also mentioned. Length of transmission line wire. Length of transmission line wire, that is something like L. Length of transmission line is L. See, for this transposed line carrying balanced currents, transposed configuration, carrying balanced currents, having some resistance value R per phase something, and having some inductance per phase. Not only that, inductance per phase, you know that LA, LB, LC, all the values are equal. And we have some capacitance per phase. Not only that, you know, capacitance from A to neutral, effective capacitance from B to neutral, effective capacitance from C to neutral. All these three also equal. Yeah, just listen to my words, what I'm saying. Just listen to my words. After getting this R per phase, L per phase, and C per phase, after getting this R per phase, L per phase, and C per phase, these three values for L length, we are arranging in a model. Right? So I can say this is the total resistance, and this is a total inductance for complete length of line L. We can say L. And the capacitance we will take half here, C by 2, and remaining half of capacitance we are keeping here. Per phase model it is. It's a per phase model, C by 2, C by 2. What we are naming this model generally? Nominal pi model. Nominal pi. Because these RLC numbers directly we are keeping into the circuit. So it is going to be called as nominal pi model, constructed for total length of line L. Constructed for the total length of line L. Okay, fine. Next. So let's continue. Let's continue like this. See, at the input side, you might be having a source, maybe a generator, assume that. At the output side, or you can say at the receiving end side, you might be having a load. So I can say we have one source at this place, something like this. And here I will have some sort of load here. Load. Right? This is a load and this is a source here. Source. I'll say voltage and currents at the sending end side, location VSIS. And voltage and currents at the receiving end side location, it will be VRIR. Receiving end side location, voltage and currents are VRIR. Next, this load is consuming a real power of PR and a reactive power of QR. So I can say it is PR plus JQR. So real and reactive powers drawn by the load. Okay, listen please. What is the aim of constructing this equivalent circuit and all? What's the aim of constructing this equivalent circuit and all? We said already at the starting of this chapter, the aim of steady state performance analysis is to know whether the transmission line is operating satisfactorily or not. To know whether the line is operating satisfactorily or not at a given loading condition. At a given loading condition means one thing we have to be clear that the load what they kept at the receiving end side must be given in the data. Means I should know the values of PR and QR as well as VR and IR. Else they will provide some of these values and we should have a capability to know the remaining numbers. Okay, so I can say this side, receiving end side, is completely known for us. Known values, receiving end side values are known for us. Okay, see, our aim is to calculate performance of line means two things we are interested to know. One is the efficiency of the line. Next one is a voltage regulation. One is the efficiency. Next one is the voltage regulation. Let us concentrate on efficiency. What is efficiency of line? Receiving end power by sending end power into 100%. Receiving end power by sending end power into 100%. Listen to me, please. Don't confuse. I will explain all the things at one point. Just listen. PR by PS. Already you know the value of PR. Now we have to get how much is the sending end real power. How much is the sending end real power? How to calculate the sending end real power? That we can calculate by using this voltage and currents. Like Vs into Is into cosine of angle between them. Vs into Is into cosine of angle between them. That will give you obviously sending and real power. And then PR by PS is going to give you efficiency of this particular transmission line. Is it clear? Please tell me up to this point what I said. Very simple. We have taken a three-phase line. For that line, I calculated resistance, inductance, capacitance for whole length of line. Okay. After calculating those RLC, we kept these things in the circuit. And I know receiving end side clearly. Load is known for us. Okay. Now, if you want to calculate efficiency, we should find out the sending end real power. And you should say PR by PS is a efficiency. PR by PS is the efficiency. Our aim is to calculate PS value. To know the value of PS, obviously VS and IS values we have to calculate. So I can say this side is an unknown side for us. This side is an unknown side for us. Okay, now listen to me. See, to calculate the sending end voltage and currents, we have to apply KVL and KCL on this circuit in a simple way. So you have to apply KCL at this node. By knowing this capacitor current, we'll find out this RL circuit current first. And then you apply KVL for this loop and you find out this voltage. After knowing this voltage, find out this C by 2 current. And then add these two currents together, you'll get the IS as well as we'll get the Vs. So simple. By the application of KVL and KCLs, we should find out the sending end voltage and currents Vs and Is. Okay, right. Next thing. For example, this is a point where you should concentrate. For example, if the load was changed, for example, you want to estimate the performance of the same line for a different load. Estimate the performance of the same line for a different load. Then what you should do? Then again, we should come back to the circuit for the changed load and you have to apply KVL, KCL and we should find out VS and IS. And then you should go for PS value and efficiency required. Again, if the load was changed, again we should come back to the network and we have to apply KVL, KCL on this network and we have to find out VS and IS, PS and then efficiency. See, my interest is to tell you, whenever that load was changed, I should come back to the network. And I have to apply KVL, KCL in order to get the values of VS and IS in each and every variation. This is laborious process. All of you getting my words? This is laborious process. So to overcome this laborious process, those KVL and KCL equations, what you are applying repeatedly, we are going to generalize those equations. Okay? Yeah. So I'll say in the next slide, just go through it. So to find VS comma IS values, KVL and KCL has to be applied. KCL has to be applied for at each time for each and every variation in VR comma IR values. For each and every variation in VR comma IR values. Okay, yeah. So let's say VR comma IR values. So this is a time-consuming process. Of analysis. Okay, this is a time-consuming process of analysis. So what we are suggesting here, tell me please what we are suggesting. We are going to generalize the KVL and KCL equations. Okay. To avoid this, KVL and KCL equations will be generalized. KVL and KCL equations will be generalized. Generalized in the sense, my interest is to write sending end voltage Vs as a function of VR and IR. Sending end current Is as a function of VR and IR. Like that we are going to write. Okay. So I can say Vs I'm going to write as a function of VR comma IR, and sending end current Is again as a function of VR comma IR. Maybe these two functions are little different. F1, F2 you say. Functions are F1 and F2. Okay. So how will be these equations you can expect now? How will be these equations you can expect? Whether these two are linear equations or non-linear equations. Whether these two equations are linear or non-linear. Definitely linear, because we are applying only KVL, KCL here. You don't find any square or cube for the voltage and currents. And moreover, your circuit is also a linear circuit. Okay. So these are linear equations. Not only that, you will get some constants in the equations, right? Vs is a function of VR and IR means you will get some constants here. Similarly, Is is a function of VR and IR means you will get some constants here. Kindly listen to me. Listen. See, whatever the constants you get in these two functions, those constants are giving relation between sending end voltage and currents to receiving end voltage and currents. The constants in these relations are going to give the relation between sending end voltage and currents to receiving end voltage and currents. Who is giving that relation in this model? Who is giving that relation between VSIS and VRIR in this model? Transmission line itself is giving that relationship. Means my interest is the constants whatever you get in these two equations is going to represent our transmission line itself. Hence, I am going to call those constants as transmission parameters. Else you can call them as generalized circuit constants of the transmission line. So I'll write like this. The constants in above equations will represent transmission line, the transmission line. Okay. Hence, these are called as transmission parameters. Transmission parameters, or you can call them as generalized circuit constants of the transmission line. else we can say ABCD parameters. ABCD parameters. I'll be taking up that in the next slide. That heading, I can say heading in the next slide. So I'm moving to the next slide. So I'll say here generalized circuit constants or you can say ABCD parameters. ABCD parameters. ABCD parameters. Generalized circuit constants, or you can call them as ABCD parameters. Okay. Yeah. So let's continue with this. See, from this point onwards, whatever the transmission line you have, this model, whatever may be the model now, is it a pi, t, long line, whatever may be the model between sending end and receiving end side, it is going to be represented simply as a two-port network. As a two-port network like this. So, like this, we are going to represent the transmission line in a two-port network model. Two-port network model. Something like this, you can say. Okay. See, this side you might be having a source, and you can call here VSIS. You can call here VSIS, and here I will be keeping load and voltage and currents at this point are VRIR. Voltage and currents at this point are VRIR. See, I'm not keeping any bar here. So like VS bar, VR bar, IS bar, IR bar, like that I'm not keeping, but you should understand that these are phasors. Voltage and currents, whatever I am showing in this figure are phasors. Means each and every number, for example, VS is having a magnitude as well as some angle. IS having some magnitude as well as some angle. Similarly, VR and IR also, right? So it's a two-port network model. Two-port network model. Yeah. So now I can say this VS is a function of VR and IR. I will be writing that VS as constant A into VR plus constant B into IR. And IS you can write as C into VR plus you can write this D into IR. IS equals to CVR plus BIR. VS equals to AVR plus BIR. And these are going to be called as generalized equations. These are going to be called as generalized equations. And I'm going to convert them into matrix form. Write them into matrix form. So you can get VSIS, voltage and currents at the sending end side, is equal to, and these are ABCD parameters. ABCD parameters, and this multiplied with VRIR. Multiplied with VRIR. So ABCD parameters multiplied with VRIR. So I think all of you know how to calculate these ABCD parameters. I think all of you know how to calculate these ABCD parameters. Yeah. What's the procedure of calculation? Procedure. First, we'll make that IR equals to 0. Open circuit will make IR current direction. This one only. IR current direction is that only. Yeah. Tell me please. Rashmi, we said Vs is a function of VRIR. So I have written Vs is equals to a constant into VR plus a other constant into IR. That's it. Okay. So Is is a function of VR and IR. So I have written Is is equals to some constant into VR plus some other constant into IR. Yeah. Listen please. Listen please. To calculate this ABCD, first I will make IR equals to 0. IR equals 0. By making IR equals 0, we will get the values of A and C. A and C. Next case I will take. I'll keep VR equals to 0 and I will be getting the values of B and D obviously. Right. So first case IR equals to 0 means we should make open circuit at the receiving end side. Open circuit at the receiving end side. Let me show. Case 1. Open circuit at receiving end side. Open circuit at receiving end side. So open circuit at receiving end side means IR is equals to 0, I should say. Receiving end current is equal to 0. So after making that receiving end current value 0, receiving end current value 0, let me copy this diagram, this one. Just look here. I'll show this diagram as a small one. So after making that IR current equals to 0 means load was removed completely. I am saying you. Load was removed completely. You no need to draw, just listen here. That's sufficient. After that load was disconnected, whatever the voltage you get at the receiving end side, whatever the voltage you are going to get at the receiving end side, that I am going to call as no load receiving end voltage of the transmission line. No load receiving end voltage of the transmission line. This is the voltage what we have to use in the voltage regulation calculation. This is a voltage what we have to use in the voltage regulation calculation. And at this time, VR is going to be called as open circuit or no load voltage of transmission line. No load voltage of transmission line. You call it as VR0. Calling that as VR0. Now, what is the sending end current value here? What is it sending end current value? Just observe now. Observe here. This is half of the charging current we mentioned. Approximately half of the charging current. This is the next half of the charging current. Half of the charging current, half of the charging current. Receiving end current is 0. Then this RL circuit what we have will carry a current of IC by 2. RL circuit will carry a current of IC by 2. Then what will happen to IS value now? Anybody tell me please? What will happen to IS value? IC by 2 plus IC by 2, that will be approximately equals to IC. IC by 2. Abhijit, you keep your networks doubt aside. Current is outgoing only. Current is outgoing. That's it. And that is charging current IC. So whatever the sending end current we have under no load condition, sending end current what we have under no load condition is going to be called as charging current. Okay. So this is going to be called as charging current at no load. Charging current at no load. Sending end current at no load condition is nothing but the charging current under no load condition. Okay. Now let's move with the equations. Let's move with the equations what we have. Vs equals to AVR plus VIR, Is equals CVR plus VIR. Let's keep IR equals to 0. Let's keep IR equals 0. So Vs you can write A into VR. Is you can write C into VR by keeping the receiving end current value 0. By keeping the receiving end current value 0. From this you can write sending end voltage is equals to A into VR0. Sending end current will be equals to C into VR0 like this. A into VR0, C into VR0. Now, what you will get this parameter A? Parameter A is nothing but Vs by VR0. Parameter A will be Vs by VR0. Similarly, C equals to Is by VR0 you can write. Yeah, please complete it. Once after completion, please raise your hands. I will move to next slide. Write that A and C. Good. So A is equals to Vs by VR0. This is one term. And that C will come to be Is by VR0 here. C will come to be Is by VR0. What's the name of this parameter A we can write and name of this parameter C. Name of the parameter A, just listen here, listen. Input voltage by output voltage. Vs by VR0, na? Input voltage by output voltage. Generally, output by input is going to be called as gain. output by input will be called as gain. It is reverse, right? So it will be called as reverse voltage gain. This Vs by VR0, we are going to name it as reverse voltage gain under no load condition. I'll say reverse voltage gain under no load condition. No load condition. Reverse voltage gain under no load condition. Okay. Yeah. Next, what is it? C we have. What is it? C we have current by voltage. Current by voltage in the sense admittance. Current by voltage in the sense it is admittance. But you see here, you are taking current in sending end port, voltage in the receiving end. Current in sending end port, voltage in the receiving end port. So you are taking these two values in different ports. Hence, it's going to be called as transfer admittance. Transfer admittance under no load. Transfer admittance under no load condition. Transfer admittance under no load condition. Or open circuit transfer admittance of transmission line. Like that also you can write. I'll write here open circuit transfer admittance. Open circuit transfer admittance. Okay, next, what is that A by C you can expect now? What's that A by C you can expect? Anybody? What is that A by C you can say? Vs by Is, na? VR0 cancel. VR0 will cancel out and it will be Vs by Is by keeping that receiving end current as 0. Vs by Is by keeping that receiving end current as 0. What is this Vs by Is actually? Input voltage by input current. Input voltage by input current means it is input impedance. Input impedance under which condition? Open circuit condition. Open circuit condition. So this you can name it as open circuit input impedance of the transmission line. Open circuit input impedance of transmission line. This you can say open circuit input impedance of transmission line. Open circuit input impedance of the transmission line. A by C. A by C we can say. So next, let's continue. Let's continue with short circuit at receiving end side quickly. Short circuit at the receiving end side, and we'll try to get the remaining two parameters and we'll make the comments on that. So second case we are taking up short circuit at receiving end side. Short circuit at the receiving end side. See, making short circuit at the receiving end side means, for example, if this is that per phase model we have, per phase model, making short circuit means I will show in a simple way, in the similar way what we have shown earlier. Yeah, you see this. So this is that short circuit what we are interested to make now. See, after making that short circuit, receiving end voltage will fall down to 0, definitely. Receiving end voltage will fall down to 0, and whatever that receiving end current we have, that we are going to name it as short circuit current at the receiving end side. That we are going to name it as short circuit current at the receiving end side. Okay, let me write. Receiving end side short circuit means VR is equal to 0, and that IR whatever we have, I will call it as short circuit current at receiving end. Short circuit current at the receiving end side. Receiving end side. Okay, let's move. I will say this word short circuit current at receiving end side as IRSC. Short circuit current at the receiving end side, I am naming it as IRSC. Let's move with that what we call ABCD equations. ABCD equations. Vs equals to AVR plus VIR. AVR 0, VIR you get. Is equals to CVR plus DIR. VR is 0, so you can get this one D into IR by keeping that receiving end voltage equals to 0. By keeping that receiving end voltage is equals to 0. And from this, you can write sending end voltage equals to V into IRSC. Sending end current is equals to D into IRSC. Sending end voltage is B into IRSC. Sending end current will be D into IRSC. Now you can get the B and D values from this. You can get the B and D values. Yeah, so let's take that parameter B. B is equals to Vs by IRSC. First term. Next, that parameter D will come to be Is by IRSC. Is by IRSC. Can you tell me what that first parameter B name? What we can say? Parameter B name. It is voltage by current, right? Voltage by current, but voltage in one port, current in the other port. Voltage in one port, current in the other port. This we are going to call it as transfer impedance. Transfer impedance. Under which condition? Short circuit. So this can be called a short circuit transfer impedance. Transfer impedance. Okay, next thing. Is by IRSC. Anybody? What you name this one? Is by IRSC. Input current by output current. Input current by output current. It can be called as reverse current gain under short circuit condition. Reverse or inverse, anything. Current gain under short circuit condition. Under short circuit condition. Okay, let's take up these this ABCD units. First, let me take B by D, then we'll go for units. What is that B by D? B by D, what you get now? Vs by Is simply. Because at IRSC will be cancelled out. Vs by Is by keeping what? By keeping VR is equals to 0. B by D is nothing but Vs by Is by keeping VR equals to 0. What we are going to name this? What we are going to name this one? It is input voltage by input current. Input voltage by input current means it's the input impedance under short circuit condition. So it is a short circuit input impedance of transmission line. Short circuit input impedance of transmission line. Let me call this one shortly as ZSC. Short circuit input impedance, we are going to call it as ZSC. 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 Already we have written open circuit input impedance, right? So you call this one ZOC. Open circuit input impedance, you call it as ZOC. Short circuit input impedance, we are naming it as ZSC. Okay, let's think about the units of these ABCD quickly. Units of these ABCD. What's the units of A? Units of A. It's voltage by voltage, right? Voltage by voltage means we don't have any units for this. So no units for A. No units for A. What about the units of C? Current by voltage, admittance, mho, or you can say Siemens. Mho, or you can say Siemens. Next. B. What's the units of B? Voltage by current. It will be ohms. Impedance. Impedance. Next. D. Current by current. No units. So A and D in the ABCD, AD will not have any units. AD will not have any units. B in ohms, C will be in terms of mho. C will be in terms of mho. So these are the units of the ABCD parameters we can expect. ABCD parameters. Next, I will introduce one small term here, which you can study in network theory maybe later, or you might have studied already. Okay, just look this term, what I'm saying. Characteristic impedance. characteristic impedance. Characteristic impedance ZC. Characteristic impedance ZC is equal to, just look at the formula what I'm saying, ZC. It will be square root of open circuit input impedance multiplied with short circuit input impedance. Open circuit input impedance multiplied with short circuit input impedance. That is a characteristic impedance formula. This you can write as square root of, what is ZOC? What is ZOC? A by C. A by C. What is ZSC? B by D. So you can write this like A by C into B by D. This is one of the very basic formula for the characteristic impedance of a network. For example, a network is given to you. Network is given. And for that network, two-port network. If they ask you to calculate the characteristic impedance, after calculating ABCD parameters, just you can say it is square root of A by C B by D. A by C into B by D. Characteristic impedance. Yes. Now let's discuss little about the properties of network here. Let's discuss little about the properties of network. First property I am saying symmetry property. When we will say the network is symmetrical, when we will say that the network is symmetrical. Symmetrical means particularly if parameters A and D are coming equal, then we are going to say that network is symmetrical. Let me write that statement. For symmetrical networks, you will be having the parameters A and D as equal. You will be having the parameters A and D as exactly equal for the symmetrical networks. Next, whereas if the network is reciprocal, sometimes can be called as passive network also, passive network. For that network, determinant of the ABCD matrix will be equals to 1. Just look here. For passive networks, or you can say pure impedance networks, or you can say reciprocal networks. You will be having that determinant of the ABCD matrix will be equal to 1. Determinant of the ABCD matrix means you have to call this like AD minus BC is equals to 1. Determinant of the ABCD matrix means you should say AD minus BC is equals to 1. The reciprocal network means the network which satisfies the reciprocity theorem. Network which satisfies the reciprocity theorem. Yeah. I will discuss about these properties, particularly symmetrical property after little time. You tell me, for example, if the network is symmetrical, if the given network is symmetrical for you, A and D will be cancelled out, and this ZC will be resulting into root of B by C. Okay. So I'll say here for symmetrical network, already we said A equals to D. Write in bracket A equals to D. So you can get this characteristic impedance as root of B by C. Characteristic impedance as root of B by C. Okay, next. So next we are going to take up a small discussion like two networks connected in cascade. Two transmission lines also you can say if you want. Two transmission lines are connected in cascade or series, or you can say tandem connection. how will be the resultant ABCD of that whole network of cascade connection. Okay, yeah. So let's take in the next slide two transmission lines. Two transmission lines connected in cascade. Connected in cascade, or you can call it as tandem connection. Tandem connection, or sometimes, particularly for transmission lines, you don't get any difference between cascade and series. You don't get any difference between that cascade and series, right? So I show two ABCD models here. So it's a first model ABCD. You can call it as A1, B1, C1, D1 ABCD parameters. And I will be showing the second model ABCD. Second model ABCD. So I'll say it is A2, B2, C2, D2. Yeah, just check this one. A1, B1, C1, D1 ABCD of line 1. Line 2, A2, B2, C2, D2. A2, B2, C2, D2, line 2. Right. So it's a line 1 and it's a line. Yeah, see this side, I am showing voltage and currents something like Vs and Is. Line 1 input side. And then line 2 output side, I am showing voltage and currents like VR and IR. VR, IR. And at the junction of these two lines, voltage and currents will be VI. VI. Voltage and currents will be VI at the junction of these two lines. VI. Next, let's move. Let's move. So I have to get the resultant ABCD of this cascade connection. In the sense, our aim is to get VSIS, sending end side voltage and currents, in terms of VRIR by taking up the resultant ABCD of the two lines in cascade. By taking up the resultant ABCD of the two lines in cascade. So these are the resultant ABCD: A0, B0, C0, D0. A0, B0, C0, D0. Those are the resultant ABCDs. Okay, listen please. So to get this resultant ABCD, just listen. I'll take line 1 ABCD and then line 2 ABCD. Just I will read out the things, just observe what I'm saying. For example, first for line 1, what you can write is VSIS equals to A1, B1, C1, D1, VI. Right? Quickly. Line 1, I am saying VSIS is equal to A1, B1, C1, D1 into VI. For line 2, input is VI. What is the output? VRIR. So you can write for line 2, VI input. ABCD of line 2 will be A2, B2, C2, D2. And this will be VRIR. So this is you call equation 1 and this you call equation 2. Simply you dump this equation 1 into, equation 2 in 1. Equation 2 in 1. Finally, what you can get in place of VI? A2, B2, C2, D2, VRIR. So you will get the multiplication of the two ABCD parameters, two ABCD matrices as a resultant ABCD parameters of the cascade connection. Following all of you. So I am writing directly now. So resultant ABCD of the cascade connection. Resultant ABCD of the cascade connection. Nothing but multiplication of the two ABCD matrices. multiplication of the two ABCD matrices. Okay, so A1, B1, C1, D1, and then multiplied with A2, B2, C2, D2 in the cascade. Yeah, so let's continue with this ABCD parameters a little bit. Some examples I'm going to take. Some examples. Just first example I'm taking now. Just listen. Some networks, I can say. Example networks. Example networks I'm taking. First network. First network. It's a simple series impedance. Simple series impedance. Like this. Simple series impedance. What will be the ABCD of this one? What will be the ABCD of this simple series impedance? It will come to be 1Z01. ABCD parameters of the simple series impedance will come like 1Z01. 1Z01. Okay, second one. Second one. Shunt impedance. Shunt impedance. Z is a shunt impedance value. Z is a shunt impedance value. And what are the ABCD of this one? What are the ABCD of this one? Shunt impedance. 1, 0, 1 by Z 1. 1, 0, 1 by Z 1. Okay. 1, 0, 1 by Z 1. Next one. Third one. We have the shunt admittance Y here. If you have that shunt admittance Y, then the ABCD parameters will be 1, 0, Y1. 1, 0, Y1. Clear? 1 Z01, 1, 0, 1 by Z1, 1, 0, Y1. So these are the ABCD of the three networks what we have shown. For the first network, just observe for the first network, you observe that A equals to D, AD minus BC is 1. A equals to D and AD minus BC 1. Second network, A equals to D, AD minus BC 1. Third network, A equals to D, AD minus BC equals to 1. See, in all these three networks, in the three networks, you know A and D are equal, and then AD minus BC value was 1. So what is the conclusion we can make from this now? What's the conclusion we can make from this now? Yeah, you have to calculate it. Kaveshri and remaining people, you take this side V1 I1 voltage and currents, this side V2 I2 voltage and currents. You apply KVL, KCL on this, and you try to find the V1 I1 relation with V2 I2. That will give you ABCD by the procedure what we have discussed. Okay. Similarly, second one and third one also. You have to do it and do it. These are simple networks. Yeah, listen please. See, if A equals to D, we can say all the three networks are symmetrical. AD minus BC is 1, means all the three networks are reciprocal. So symmetrical and reciprocal networks you can say. Symmetrical and reciprocal networks. Symmetrical as well as reciprocal networks. Yeah. Next thing. So I'm taking the fourth example as a cascade connection. Fourth example I am taking as cascade connection. Just look here. Cascade connection. So in this cascade connection, what I'll do is I'll take this series impedance first. I'm taking this series impedance first. Network 1. Network 2, I'll take the shunt admittance. Network 2, I am taking this shunt admittance. Okay. So like this, I'm taking up. So you say, so this is network 1 series impedance and network 2 shunt admittance connected in cascade. Connected in cascade. And what will be the resultant ABCD of this? What will be the resultant ABCD of this one? A is not equals to 1 by D. A is not equals to 1 by D. See, in this case, you have to take ABCD of network 1, ABCD of network 2, and we should multiply them in order to get the resultant ABCD of that cascade connection. So I can say resultant ABCD of this cascade connection. ABCD, I will write simply ABCD. First, for the network 1, you write 1Z01. 1Z01. And then for network 2, 10Y1. 1Z01. Next one will be 10Y1. You multiply these two matrices together. Multiply these two matrices together. You'll be getting like 1 plus Z by ZY1. 1 plus Z by ZY1. Okay. Like this, you will be getting ABCD of this cascade connection. And you observe now, parameters A and D are unequal. So this network is unsymmetrical network. A and D are unequal. Network is unsymmetrical. Network is unsymmetrical. And AD minus BC, if you calculate, how much is that AD minus BC? AD minus BC, that will come 1. So network is still reciprocal. Network is still reciprocal. Unsymmetrical, but it is reciprocal, we are saying. Unsymmetrical. Kalyan, that's what I said. You take that as a two-port network and you have to calculate it kindly. We have to calculate it. V1, I1, you should take on one side. V2, I2, voltage and currents on the other side. Apply KVL, KCL, you will get the ABCD. Follow the procedure of ABCD. Yeah, listen to the comment what I am making now. Listen to the comment. First, network 1. Network 1. Is it symmetrical or not? Network 1, is it symmetrical or not? Tell me please. Network 1, is it symmetrical? Yes. Because you get A equals to D for network 1 symmetrical. What about network 2? Network 2. Is it symmetrical or not? Network 2. Yes, that's also symmetrical. See, the thing here, network 1 symmetrical, network 2 symmetrical, but cascade connection is coming as unsymmetrical. Network 1 symmetrical, network 2 symmetrical, but cascade connection of these two is coming as unsymmetrical. Means, can we make a comment? Can we make a comment that always, listen to me, always, if I connect two symmetrical networks in cascade, resultant will become unsymmetrical. Can we make that type of comment? Yes or no? No, we can't make it. We can't make it. For example, I'll say one more cascade connection, something like this. So this is Z1 impedance we have. Z1 impedance. And this is Z2 impedance we have. Z2. So it's a network 1 and it's a network 2 connected in cascade. Resultant will come to be what? Obviously, so network 1 symmetrical, network 2 symmetrical, overall network will also be symmetrical in nature. Symmetrical in nature. So I'll say, if two symmetrical networks in cascade, two symmetrical networks are connected in cascade, then the resultant network may or may not be symmetrical. May or may not be symmetrical. May or may not be symmetrical. Then the resultant network may or may not be symmetrical. So I think all of you getting this point, what I'm saying. Resultant network may or may not be symmetrical. Yeah, listen. So then I will try to tell you this one, just listen. So without doing all these calculations, how can I say whether the network is symmetrical or unsymmetrical just by looking at it? Just by looking at that, how I can say, is it a symmetrical network or unsymmetrical network? Means, listen. If the network looks to be same on both sides, then it will be symmetrical. Okay, for example, it's a port 1 you take, port 1, it's a port 2. Port 1, port 2. First you should trace from port 1 to port 2. Port 1 to port 2. Then you trace from port 2 to port 1. If the trace is same in both directions, then you can call it as symmetrical one. For example, if I say from port 1 I am starting, port 1. First I will have series impedance. Number 1, series impedance. Next I will have shunt admittance by number 2, shunt admittance. That's it. That's a sequence. Next, if you come from port 2 to port 1, number 1, shunt admittance. Number 2, series impedance. Sequence is different, right? That order is different. Order of the elements is different. So obviously, this network will be unsymmetrical in nature. All of you understood the thing what I said? Please tell me. Yeah. So just you have to trace the elements from one side to other side. From 1 to 2 you should trace. And again from 2 to 1 you should trace. If the trace is same on both sides, then it will be symmetrical. Else it is unsymmetrical. For example, this network, a single element Z. So from 1 to 2, if I see Z, 2 to 1, again Z, it will be symmetrical. For example, yesterday we discussed many networks, right? Just tell me about some of these things. Tell me, receiving end capacitor model. Receiving end capacitor model, is it a symmetrical one or unsymmetrical one? Receiving end capacitor model, unsymmetrical, definitely. First I am seeing RL, then C. From other side, if you come, first C, then RL, not C. Sending end capacitor model, first C, RL, next from other side, RL, C, not C. Middle end capacitor model, first I am saying R by 2, L by 2, next C, next R by 2, L by 2. From other side, R by 2, L by 2, C, R by 2, L by 2. Looking at same, means nominal T model is a symmetrical one. Next, nominal pi, also symmetrical model. C by 2, RL, C by 2. Other side, C by 2, RL, C by 2. Following all of you. So this is one of the easiest way of identifying whether the network is a symmetrical network or unsymmetrical network. Okay, let's think a little more about this cascade connection. First comment what we are making is, if two symmetrical networks are connected in cascade, resultant network may or may not be symmetrical, which we can't say. For example, if two reciprocal networks in cascade, passive networks, reciprocal networks in cascade are in cascade, then what we can say, then the resultant network will be always reciprocal. Then the resultant network will be always reciprocal. Then the resultant network is always reciprocal. Because both networks are consisting only passive elements, right? And obviously resultant network also consisting passive elements. Yes, Shiv Prasad, we should take only RL. That's it. So, an example of Z1, Z2 seeing from different ports, you take summation. Sweta, you take summation. If there is a series element, you have to sum up them. Z1 plus Z2, you take Z1 plus Z2. Okay. You take Z1 plus Z2. This combination Z1 plus Z2, and this network is looking as a single element network of Z1 plus Z2. Then it will be definitely symmetrical. Yeah. Reciprocal means network consisting only passive elements. There is no source. There is no source inside the network. You might be having source only at the ports. You might be having source only at the ports. Okay, yeah. Next, let's think little about the transmission lines connected in parallel. Means two ABCD networks connected in parallel. How will be the resultant ABCD? And we will recall these properties of symmetry and reciprocity. Transmission lines. Two transmission lines connected in parallel. Connected in parallel. Two transmission lines connected in parallel. Let me show first first ABCD network A1, B1, C1, D1, and then the second ABCD network, something like this A2, B2, C2, D2. Calling like this A1, B1, C1, D1, first network. Second network is A2, B2, C2, D2. Yeah. So I'll say here like this we are showing. So these two lines we have to connect in parallel as we said just now. These two lines we have to connect in parallel. Yeah. So on this side, you'll have VSIS, and on the other side we have VRIL. VRIL. VSIS, VRIL. And ultimate aim here is to express sending end side voltage and currents in terms of resultant ABCD of parallel connection. Resultant ABCD of the parallel connection. Resultant ABCD of the parallel connection. Of course, you know these values of A0, B0, C0, D0 will come in terms of line 1 and line 2 ABCD. Line 1 and line 2 ABCD. Okay, so I'm going to give these four values A0, B0, C0, D0 in terms of A1, B1, C1, D1 and A2, B2, C2, D2. Okay. So I'm not going with any derivation. Directly I'm going to give these terms in terms of the line 1 and line 2 ABCDs. So I'm moving in the next slide to take up the A0. So resultant ABCD parameters. Resultant ABCD parameters. First I'm writing A0. So it will be A1 B2 plus A2 B1 by B1 plus B2. A1 B2 plus A2 B1 by B1 plus B2. That is the resultant parameter A0. Resultant parameter A0. Next, resultant parameter B0 I am writing. It will be like B1 B2 by B1 plus B2. B1 B2 by B1 plus B2. Next, resultant parameter C0. C0. C1 plus C2. C1 plus C2 plus A1 minus A2 into D2 minus D1 by B1 plus B2. A1 minus A2 into D2 minus D1 by B1 plus B2. Like the same. That's the C0. C0. Next, D0. D0. It will be D1 B2 plus D2 B1 by D1 B2 plus D2 B1 by B1 plus B2. D1 B2 plus D2 B1 by B1 plus B2. D1 B2 plus D2 B1 by B1 plus B2. Receiving end current will be outward only. It's not inward. Receiving end current will be outward. It's not inward. Okay. So next, I will be extending this one. For example, if the two lines which we are connecting in parallel, these two lines, if these two are identical, identical means A1, A2 equal, B1, B2 equal, C1, C2 equal, D1, D2 also equal. Okay. If the two lines are identical, if the two lines are identical, identical means A1, A2 equal, B1, B2 equal, C1, C2 equal, D1 and D2 also equal. A1, A2, B1, B2, C1, C2, D1, D2 are equal. Then the resultant ABCD will be just check this one, A0. What will happen to value of A0? What will happen to A0 value? Just check here. A1 B2 plus A2 B1 by B1 plus B2 na? Okay. Already we said 2 and 1 are same. 2 and 1 are same. Simply whatever the 2 we have B2 A2 that you replace with B1 A1. So what you get now? A1 B1 plus A1 B1 by B1 plus B1. So it will come to be 2A1 B1 by 2B1. So from this you can call this A0 value either A1 or A2. A0 value is either A1 or A2. That's the A0. Next, what is B0? What is B0? Check here, B0. B1 B2 by B1 plus B2 means it is B1 square by 2B1. So it's B1 square by 2B1. B1 square by 2B1 means this B0 will come to be either B1 by 2 or you say it is B2 by 2. B1 by 2, else you can say it as B2 by 2. B1 by 2, B2 by 2. Next, what is C0? What is that C0 we have? Tell me, C0. C1 plus C1. So it will be 2C1 and this will be 0. Na? A1 minus A1 0, D2 minus D1 also 0. So this is 0. So you get 2C1 or you can say 2C2. No issue. C0 will be either 2C1 or you can say 2C2. Next, what is D0? What is D0 here? Tell me please D0. D1 B1 plus D1 B1 by B1 plus B1. So it's 2 D1 B1 by 2 B1. 2d1 b1 by 2b1. Means you can get this d naught value as either d1 or d2. D naught value you are going to get like either d1 or d2. Either d1 or d2. So like this, we will get the resultant ABCD parameters. Parameter A naught is equals to either A1 or A2. Parameter B naught will be B1 by 2. Parameter C naught is equals to 2C1. Parameter D naught is equals to either D1 or D2. D1 or D2. Okay. So simple. A resultant parameter A naught is not going to be changed. Resultant parameter A naught is not going to be changed, but parameter B naught will become half. Means B naught will become half of the original value, and C naught will be double the value. Double the value. Okay, listen. Stop writing, all of you. Just check back to the ABCD parameters calculation what we have made. ABCD parameters calculation what we have made here. Just see this from beginning. This is the heading we have taken. We have written VSIS equations like this. And in matrix form, we'll get like this. First, we said we have to take open circuit at receiving end side. There you get parameters A and C. And then we have gone for short circuit at receiving end side. There you got these parameters B and D. Okay. So after that, we say characteristic impedance and all. Then we have moved to cascade connection and parallel connection. Cascade connection and parallel connection. Yeah, listen to me. See, before moving to the cascade connection, parallel connection and all, let me make some more comments on this ABCD with respect to transmission line wire. With respect to transmission line wire. Very simple comments we are going to make here. Okay? Yeah. So I'm taking a new slide in between. Just listen. Look here. Look this example what I am talking. A practical transmission line. As assume that we don't have any resistance for time being. Series resistance we don't have, as series inductive reactance. XL 50 ohms. Shunt capacitive reactance XC 2000 ohms. Shunt capacitive reactance XC 2000 ohms. Forget about all the things. Just listen whatever I am saying. You just listen. Series inductive reactance 50 ohms. Shunt capacitive reactance is 2000 ohms. Now, could you please tell me what is series impedance value? Series impedance value J50 ohms you can write. JXL na. JXL in the sense it will be J50 ohms. And what is the shunt admittance value? Shunt admittance value was 1 by minus JXC. 1 by minus JXC in the sense 1 by minus J 2000 in terms of mho. 1 by minus J 2000 in terms of mho. Class will be up to 9:30. Class will be up to 9:30. Listen to me. Let's take up two exercises what you have done. First, I will draw the pi model of this line. I will be drawing the pi model of this line. Okay? Yeah. Look here. Pi model of the line I am drawing. Yesterday we discussed one problem also, right? That problem pi model you can say this. J50 ohms. JXL. is minus j to xc, na? Impedance. So minus j 4000 ohms. It will be again minus j to xc. It will be minus j 4000 ohms. Minus j 4000 ohms. So let me copy the same diagram, which I need to repeat further. Done. Listen now. See, we have done two cases earlier, right? First case, it is open circuit. Second case, it will be short circuit. I am taking open circuit first. Open circuit at receiving end side. So I'll keep some source here first. I'll keep some source here. And this is open circuit, means IR value 0. And this is VR 0, something like this you have. And here you have VS sending an voltage, VS. And this current is IS. That current is IS. Okay. See, already I mentioned one statement that series reactance value was negligibly small compared to shunt element. Series reactance value was very, very low compared to shunt element. That comment already I have made. XL is very, very less compared to XC. Else you say XC is very, very large compared to XL. Okay. So that's why you see the series element negligible and shunt element is very large. How these two are connected? All of you, tell me please, how these two are connected? J50 and minus J4000, how these two are connected? Series. Connected in series. Because I don't have any other element above that, right? These two are in series. Okay. After saying that these two are in series, what is the resultant? Minus J 3950. Minus J 3950. That is approximately minus J 4000 only. Minus J 3950 is close to minus J 4000. And that minus J 4000 will be in parallel. Minus J 4000 will be in parallel. What's the resultant now? Minus J 2000. Minus J 2000. Means my interest is with respect to this point. If you look at this impedance calculation, impedance calculation, that is coming as minus J 2000 ohms. Minus J 2000 ohms. All of you getting me? All of you getting this? Okay, next thing. What is voltage at this node? What's the value of voltage at this node? That's VS, of course, correct. VS is a voltage, that's okay. But I can say this voltage approximately VR0. I can say that voltage approximately VR0. Yes or no? Approximately, because this by doing this division, the total voltage might appear across this 4000 ohms only rather than 50 ohms drop. Right. So this will be approximately equals to VR0. Next thing. Now, what is that? Listen, please. What is that? VR0 by IS. What is a VR0 by IS approximately? That's what you are saying now, voltage to current ratio. That's what you are saying now, voltage to current ratio. What is that? Tell me please. VS by IR0 approximately equals to how much? Minus J 2000 ohms. Minus J 2000 ohms in this particular calculation. Minus J 2000 ohms in this particular calculation. Approximately. Yeah, this point you should be very clear. All of you understood this or not? I need your response. Have you understood this or not? Good. Listen. I'm saying you again. Listen. The series reactance value was negligibly small compared to shunt element. So if you take up series combination of these two, that will be coming very close to minus J 4000 only. So minus J4000 minus J4000 will come in parallel. Resultant will be minus J2000. So impedance seen with respect to this point will be minus J2000. Impedance seen is minus J2000. Generally, what is the formula for impedance seen? Voltage to current ratio. Voltage to current ratio. As this minus J50 is negligibly small, this VR0, what we say here, this point voltage and this point voltage might be almost equal. Okay, so because major voltage will appear across only 4000 ohms rather than 50. So this node voltage will be written approximately VR0. Approximately VR0. Now, voltage to current ratio at this point is nothing but VR0 by IS. VR0 by IS. That value is equals to impedance what you said just now. That is minus J2000. Now all of you clear now? Tell me please. I've explained just now. Yeah, fine. Next, a small extension. Look here. Inverse it, reverse. You write it as IS by VR0. 1 by minus J2000. IS by VR0, you will get it as 1 by minus J2000. What is that IS by VR0? What is that IS by VR0? See, IS by VR0 is a parameter C. And that C is approximately equals to, what is it? 1 by minus J2000. What is it? 1 by minus J2000. Shunt admittance of transmission line. 1 by minus J2000 will be shunt admittance of transmission line. Clear? Shunt admittance of the transmission line. This is the result what you are getting from the open circuit analysis of transmission line. Transmission line, not the network what you draw simply in network analysis. Okay, let's think about short circuit also and we'll make some comment. Short circuit. Second one, short circuit. Short circuit study. You see this? This is a place where you have a voltage of Vs. Voltage of Vs. Current you have something like Is, and you are going to make one short circuit at this place. Short circuit. And you are saying this VR is equals to 0. You are saying that VR is equals to 0 at that place. VR equal to 0 at that place. Next thing, listen please, listen. This is the current you are saying as IRSC. This is the current you are saying as IRSC, and this node voltage is Vs. Node voltage is Vs. This node voltage 0 na, because of short circuit. This node voltage will be 0. And what is the capacitor current? 0. Capacitor current will be 0. Then what is current flow in the J50? What is current flow in the J50? IRSC. Current flow in the J50 will be IRSC. Yes or no? Current flow in the J50 is IRSC. So just you look in this element itself, in this element. Vs minus 0 by J50 is the current. Is that correct? Is that correct? So you can get this Vs by IRSC like J50. Vs by IRSC, you will be getting like J50. What do you mean by Vs by IRSC? Vs by IRSC is what? Tell me please. That is nothing but the parameter B. Vs by IRSC is nothing but the parameter B. And what is J50? Series impedance of line. Series impedance of the transmission line. That's the J50. J50. Voltage is 0, current is 0. That's it. Applied voltage is 0 across this capacitor. So current will be 0. So tell me now, if you calculate ABCD parameters of a practical transmission line wire, ABCD parameters of a practical transmission line wire, parameter B representing what? Parameter B representing what? Series impedance of the transmission line. Series impedance of the transmission line. And whereas the parameter C is going to represent the shunt admittance of the transmission line. So this statement what I am making now, is valid only for practical transmission line systems. Okay. So I'll write the comment now. For practical transmission lines, parameter B represents the series impedance, and parameter C representing the shunt admittance, How it is happening means, because that series reactance is very, very less compared to the shunt element. Our shunt element is a bit large compared to series element. Yeah, all of you understood this? Please tell me. This comment what we made, have you understood this one? This is one of the very important thing to understand. Good. Yeah, fine. Next thing, let me continue like this. See, for example, two identical transmission lines are in parallel. Just listen to my words, please. Valid for any line. Reverse voltage gain, reverse current gain goes to a different terms. That's it. Reverse voltage gain is a different term. Reverse current gain is a different term. Just listen to me. What I'm saying. See, for example, two identical lines are in parallel. Then definitely I can say series impedances will be in parallel. Shunt admittances will be in parallel. Series impedances will be in parallel. Shunt admittance also in parallel. If two impedances in parallel, equal impedances in parallel, what's the resultant? What is the resultant impedance if two impedances in parallel? It will become half. That's why the parameter B is becoming half now here. That's why this parameter B is becoming half. Are you getting this one? If two identical lines are in parallel, resultant series impedance will become half. That's why this parameter B is becoming half. Similar statement. If two identical lines are in parallel, two equal admittances will be in parallel. So that's why the admittance will become double. Shunt admittance will become double, and parameter C also becomes double. Following all of you. So as a parameter B is representing series impedance and C is representing shunt admittance, if two identical lines are in parallel, B becomes half, C becomes double, but you don't have any change in the parameters. A and D don't have any change in the parameters. A and D. Okay, next thing. One more simple thing. Observe now. Two lines in parallel, that's it. Two lines in parallel with impedances Z1, Z2. Two lines in parallel with impedances Z1, Z2. Resultant will be Z1, Z2 by Z1 plus Z2. Z1, Z2 by Z1 plus Z2. What have here? B1, B2 by B1 plus B2. Z1, Z2 by Z1 plus Z2. B1, B2 by B1 plus B2. That's the resultant B0. Okay. Similarly, two lines in parallel with admittances Y1, Y2, shunt admittances. Y1, Y2. What's the resultant? Y1 plus Y2. Y1 plus Y2. Here, C1 plus C2. C1 plus C2. And you see, this value what we have, A1 minus A2 into D2 minus D1 by B1 plus B2, this number will be negligibly small for practical transmission line. It's very low. Negligible for practical lines. Practical lines. For practical transmission lines, that number will be negligibly small. Negligibly small. Okay. Next thing. Next. See this. See earlier in the cascade connection we discussed one time. Cascade connection. I am going to that slide to show that comment. What you have written here in cascade connection. If two symmetrical networks are connected in cascade, resultant network may or may not be symmetrical. May or may not be symmetrical. Now you tell me, if two symmetrical networks are in parallel, how is the resultant? If two symmetrical networks are in parallel, then the resultant network will be, tell me please, resultant network will be definitely symmetrical. Resultant network will be definitely symmetrical. Resultant network will be definitely symmetrical. Okay, symmetrical. How in the sense, just I will tell you, A1 equals to D1 you are saying now, network 1 symmetrical. Network 1 symmetrical means A1 equals to D1. A2 equals to D2 means network 2 is symmetrical. Network 2 is symmetrical. Now what is the value of A0? What's the value of A0? Just to check the formula. This is a formula for A0, right? This is a formula for A0. I'm showing here. It's a formula for A0. Now, whatever that A1 you have, that you replace with D1. This A1 you replace with D1. A2 you replace with D2. What you will get now? D1 B2 plus D2 B1 by B1 plus B2. This is a value D0. Means if A1 equals to D1 and A2 equals to D2, then obviously A0 and D0 values will be equal. Then obviously your resultant network will be symmetric. Resultant network will be symmetric. So I think all of you understood this cascade connection and parallel connections. Is it okay? Yeah. So just definitely symmetrical only. What to check here again? If two symmetrical networks are in parallel, then the resultant network will be definitely symmetrical. Yes, correct statement only. What's doubt in that, Bhaskar? Yeah. See, this is a procedure I have mentioned in the yesterday class. First, we have gone with the classification of lines. You have to remember. We have to remember that A0 and B0 formula. I think B0 and C0, writing those two will be easy. Writing the A0 and B0 will be easy. Sorry, B0 and C0 will be easy. But you have to remember that A0 and D0. A0 and D0. You have to remember it because it is one of the untapped area in the examination. Asking question on the parallel lines. Okay, next, listen. This is a procedure I said. First, we have gone for classification of lines, short, medium, and long, and we have seen equivalent circuits of that. After taking up the equivalent circuits, we have introduced the ABCD parameters to make our analysis easy. Now, we will move back to classification of lines. Means we'll take up each and every line separately now. First I'll take up short line, that analysis we'll do. Then medium line, that analysis. Long line, that analysis. ABCD parameters of each and every one. And finally, we make our comments. Okay. So I have a break for 5 minutes. So I have a break for 5 minutes. After that break, I will be continuing with the short transmission line study. Short transmission line analysis we are going to start. Okay. So even though I say 5 minutes, I will be coming after 10 minutes only. Okay. Fine. So I have resumed the audio, video, and screen. Right. So let's continue with the short transmission line analysis in the next slide. Next topic, you can say this one. Short transmission line analysis. Short transmission line analysis. Yeah, see this. This one. See, in case of short transmission line, we don't have the shunt element. Only that. We don't have the shunt element. We have series resistance as well as series inductive reactance, both. So I will be keeping that short transmission line in a per phase model like this. RL circuit, RL, and this is a sending end side, Vs, I can say, and current is Is, and receiving end side, it is VR voltage, and current here is IR. Current is IR. Next you see. This series combination of RL, I'm going to call as series impedance Z. Series impedance Z. That Z is nothing but R plus J omega L. Z is equals to R plus J omega L. Else you can call R plus JX. JX suffix. L is suffix. Reactance, inductive reactance. At this side, you might be having one voltage source. And this side, you might be having a load. This side, you might be having a load. Okay, voltage source and load. Listen to this. As a basic analysis here, you apply KVL for this loop. What you will get? KVL for the loop. KVL for the loop. It's the input voltage Vs. Is into Z is the drop. VR is also drop. So I can say sending end voltage Vs minus drop in this impedance is Is into Z minus receiving end voltage VR, that is equal 0. Loop. KVL for that loop will give you Vs minus Is into Z. Yeah. Is into Z minus VR equals 0. Means you can write here sending end voltage will be equal to VR plus. See, in place of Is, you can write IR, right? Because Is and IR both are exactly equal. So it will come to be IR into Z. Vs is equals to VR plus IR into Z. Already Is equals to IR. Sending end current equals to receiving end current itself. You can write it as 0 into VR plus IR. You can write that sending end current as 0 into VR plus IR. So by using these two, we can get the ABCD parameters. Like Vs equals to AVR plus VIR, Is equals to CVR plus DIR. So I can say in the next slide, sending end voltage and currents, VSIS is equal to ABCD multiplied with receiving end side quantities VRI. And here you can get 1Z01. 1Z01. And you observe now, A and B values are equal. So obviously, already we studied that if you have a simple series impedance, it is a symmetrical model. So A equals to D. So I'll say network is symmetrical. Symmetrical network, we can say. And then AD minus BC value is 1, you can observe here. So your network is reciprocal. Okay. A equals to D, symmetrical network. AD minus BC is 1. And it will be reciprocal network. Okay, next thing. What is the expression for voltage regulation? Voltage regulation expression. Voltage regulation expression. Already we have said that equation in the previous class, that is mod VR0 minus mod VR by mod VR. Voltage regulation expression in general. In general, it will be coming like mod VR0 minus mod VR by mod VR. Okay. See, this mod VR0 is a no load receiving end voltage of line. No load receiving end voltage of line. So first we will do some sort of generalized calculations. Generalized calculations, and then we'll come back to this equation. Okay. Yeah. Please go through it, what I'm saying. Please go through it. At no load operation. No load operation. At the no load operation. Yeah. Listen, please. Listen, please. At no load operation, receiving end current is equals to 0. Receiving end current is equals to 0. Okay. Then what is Vs? What is Vs? See, you have to tell this one from generalized one, not from the short transmission line. Not from the short transmission line. You should say from ABCD equations. You should say it from ABCD equations, I am asking. Vs is equals to A into VR. VR0, in fact. And what is Is? C into VR0. Okay. Vs equals to A into VR0. Is equals to C into VR0. And this Is what we have here, this itself we have named as charging current. This itself we have named as charging current. We'll take up that. We'll take up that. And you know, from this, VR0 value is nothing but Vs by A. No load receiving end voltage of the transmission line is equals to sending end voltage by parameter A. Sending end voltage by parameter A, we can say. Okay. Yeah. So now I will say Is, or else you can say charging current at no load. Charging current at no load condition. At no load condition. IC per phase is nothing but sending end current phase at no load operation. Sending end current phase value at no load operation, that will be coming like C into VR0 phase. C into VR0 phase. Okay, IC phase is nothing but C into VR0 phase. What is it VR0 phase? You can write. It will come like Vs phase by A. It will come like Vs phase by A. Okay, so I can write in the next slide. Next slide. Charging current per phase is nothing but C into Bs phase by A. Charging current per phase is equals to C into Bs phase by A. IC per phase equals to C into VR0 phase. VR0 phase is nothing but Vs phase by A. Now, what is voltage regulation equation you can write? What is that voltage regulation equation? Mod VR0. That VR0 you can replace with Vs by A, and you have VR. Okay, fine. So you'll write voltage regulation equation now. It will be modulus of Vs by A minus mod VR by mod VR. Voltage regulation equation, mod Vs by A minus mod VR by mod VR. So I'm asking one very simple question. I'm asking this very simple question. Whether this voltage regulation equation is valid for all cases or not. Whether this voltage regulation equation is valid for all cases or not. Can I use this one for medium line and long lines? Can I use this one for medium line and long lines? Yes, we didn't take up the short transmission line anywhere in this discussion. In this discussion, we didn't take up the short transmission line anywhere. Just I have taken the generalized equations of ABCD, and we came to know the voltage regulation equation like mod Vs by A minus mod VR by mod VR. This equation is a generalized equation for the voltage regulation, which can be used for any transmission line. Any transmission line. Similarly, charging current also. Similarly, charging current also. These are generalized equations. Generalized equations and can be used for any transmission line. Can be used for any transmission line. Can be used for any transmission line. Okay. Now, exclusively for short line, if you talk, exclusively for short line, if you talk, for short line, you know, parameter A is 1 already, and parameter C is 0. Parameter C value 0, just to observe in the ABCD. A equals to 1 and C equals to 0. If that's the case, charging current per phase will come to be 0 here. And voltage regulation will be coming like magnitude of the sending end voltage minus magnitude of the receiving end voltage by magnitude of the receiving end voltage. A is equals to 1, we substitute here. So we'll get mod Vs minus mod Vr by mod Vr. This is a voltage regulation equation. That's a voltage regulation equation. For short line, I will try to modify this one. Means we will try to approximate this value, approximate this term Vs minus Vr, particularly mod Vs minus mod Vr. We'll try to approximate it. Yeah. So I'm showing previous slide. If anybody is still writing, please complete it. Previous slide. So for that approximation mod Vs minus mod Vr, I'm going to take up the phasor diagram. So I'm going to draw the phasor diagram. By using that phasor diagram, we'll try to take up that mod Vs minus mod Vr. Yeah. So I'll say here phasor diagram for this short line model. Phasor diagram for short line model. First to tell me, according to our short transmission line study, which are the known values and which are unknown values here? VR, IR will be known numbers. VS, IS will be unknown numbers. Clear? So VR, IR are known numbers, we are saying, known numbers. These two are known phasors, you can write. Known phasors. VR, IR will be known phasors, we can say. And what is it VS and IS now? What is it VS and IS? That will come in terms of VR, IR. Na? What is VS you write? VS. That's what you got from KVL, right? KVL. VS equals to VR phasor plus IR into Z. So you write is VR plus IR into Z is what? R plus JXL. Z is nothing but R plus JXL. So you can write this like VR plus IR into resistance plus IR into JXL. IR into JXL. Or else you write J into IRXL. Like that you can put. J into IRXL. That's the sending end voltage. That's a sending end voltage. Next thing. IS equals to IR anyhow we have, that will take up. See, from these two known phasors, VR and IR, I'll tell you first, receiving end power factor. Receiving end power factor, or you can say load power factor also. Cos pi r, lagging. So I'll say cos pi r lag is a receiving end power factor. Receiving end power factor. Okay. See, from these two known phasors, VR and IR, one you should take as reference. One among these two known phasors we should consider as a reference. In this analysis, I am considering current as a reference phasor. For easiness in understanding, I'm taking receiving and current as a reference. Chosen as a reference. Reference phasor. Reference phasor. So let's start drawing the phasor diagram. First, I will show IR phasor, then VR phasor, then we will try to take up the VS phasor, right? And then IS phasor. And we will make some comments on that, and we'll try to take up the mod VS minus mod VR from that we dump into the voltage regulation equation. Okay? Yeah. So just have a look in the next slide. So first I am going to show the VR, IR phasor as a reference, something like this. It's a receiving end current I am showing. Receiving end current phasor IR. Reference. Next, how will be the receiving end voltage? How will be the receiving end voltage VR? Tell me please, how is a VR? Is it leading or lagging? See, power factor we are saying lagging now. Power factor we are saying lagging means IR will be in lagging with respect to voltage. IR will be in lagging with respect to VR. So I can say definitely VR will be leading. Receiving end voltage will be in leading. So I'll show here. This is a receiving end voltage to be expected. This is the receiving end voltage to be expected. And this angle gap between these two is phi r. Angle gap between them is phi r. This one. Next. Next. For that IR. Sorry, for that. No, you should not say that, Siva. You should not say that. It depends upon load. It depends upon load. Next thing. See, for this VR phasor, I should add two things. One, IR into R. Next one, J into IR into XL. These two we have to add. So what is the angle of IR into R? The angle of this IR into R will be angle of IR only, na? The angle of IR into R will be angle of IR only. So I will show that IR into R in this manner. IR into R in this manner. Okay. So next, IR into XL. IR into XL multiplied with J. It will be 90-degree leading. It will be 90-degree leading. So obviously you are going to get that IR into XL something like this. So it is J into IR into XL. J into IR into XL equals J into IR into XL, but this magnitude will be IR into XL. Now we have to take up this VR, IR into R, IR into XL, summation. That summation will give you the sending end voltage. That summation will give you the sending end voltage. Sending end voltage. Okay, next. Already you know sending end current and receiving end currents are equal. Sending end current and receiving end currents are equal. So whatever the IR we have, that itself you can call it as IS. And angle between VS and IS. Angle between VS and IS, this we are naming as sending end power factor angle, phi s. Phi s is the sending end power factor angle. Sending end power factor angle. Not only that, you observe now this cosine of this phi s, not that, phi s is greater compared to phi r. That's the observation from this phasor diagram. From this phasor diagram, you observe that phi s is greater compared to phi r. Not only that, cosine of that phi s is less compared to cosine of the phi r. Cos phi s is less compared to cos phi r. Cos phi s is less compared to cos phi r. Okay. Next. Let's continue like this. What is this angular difference? What is this angular difference you can observe? It will be phi s minus phi r. This angular difference will be phi s minus phi r. Phi s minus phi r. Okay. Next. Just have a look here. IR into XL we have mentioned. Next, let's look here. So I'm extending this VR phasor. I'm extending the VR phasor little above like this. I've extended the VR phasor like this. Now, simply what you do is, You try to take up the VS phasor onto this VR. Try to take up the VS phasor onto this VR. Then we will try to go with a comparison. Okay. So what is that VS phasor taken onto VR? VS phasor taken onto VR. This is a point O, you can say, and this is the point A. OA. 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 See, you see, it's a right angle triangle. Na? It's the right angle triangle. And from this OA will be equals to VS into cosine of pi s minus pi r. VS into cosine of pi s minus pi r. That's the OA length. OA length. Let me write. Let me write the next slide. So I am saying from phasor diagram, from that phasor diagram, OA is equals to VS magnitude into cosine of angle. Cos of pi s minus pi r. Cos of pi s minus pi r. Next thing. Let me call this point as B here. This point will be. Then what is that OB length here? Mod VR. OB length is nothing but mod VR. OB length here is mod VR. Now, if you are capable to get this BA, BA length, then obviously you can write this OA equals to OB plus BA. OA equals to OB plus BA. By that, you try to get that mod VS minus mod VR. By that, you can get easily what is that mod VS minus mod VR. That's our aim now. That BA length you have to calculate now. Okay, all of you remember this. What's our aim? To calculate this BA length. That's it. Next, let's look back. Look back here. I'm showing some one more line. I'm showing one more line. Just observe. This is that line I am showing here. That's a one more line I'm showing. And what is this line length you can experience? What is this line length you can experience? IR into Z. IR into Z. I'll show you. This point B we have shown A. Okay, C, D. C, point C, and this is a point D. How is it BCD triangle looks to be for you? How that BCD BCD triangle looks for you? It's a right angle triangle. Okay, not only that, it is identical to impedance triangle. Yeah. See, this BCD triangle, it's a right angle triangle. Not only that, it is identical to impedance triangle. Okay. So I'll show here impedance triangle. Impedance triangle. So this is resistance I'm showing, and this was reactance. Okay, and this is impedance mod Z. So it's R X, and this is mod Z, which is root of R square plus X square. Root of R square plus X square, and let me call this angle is theta. That angle is theta. That theta is going to be called as impedance angle of transmission line. Theta will be called as impedance angle of transmission line. Impedance angle of the transmission line. Okay, that theta is going to be called as impedance angle of transmission line. Next, let's move to this one. So this is that theta angle, I can say. This total angle is theta. The total angle is theta. And what is that BD length we are saying? BD length is magnitude of IR into magnitude of Z. Magnitude of IR into magnitude of Z. Yeah. All of you following this till now? Till now, all of you following this one? Please kindly respond. Okay, listen now, listen. I'm asking one small question to you. What is this angle? Anybody, can you tell me what is this angle? This angle is phi r, right? That angle is equals to phi r. Right? Receiving end power factor angle, phi r. Okay, good. Now, what is this angle? What is this one? Theta minus phi r, na? This angle will be theta minus phi r. Now, how is that triangle? Yeah. How is this? Triangle ABD looks to be for you. How is a triangle ABD looks for you? Right angle triangle. Triangle ABD is a right angle triangle. What's the aim here? With what we are discussing all these things? What's the necessary of all these things here? Why we are discussing all these things here? Anybody? To calculate BA. Calculate BA, we are doing all these things. Now you see, this BA length is nothing but BD into cos of theta minus phi r. From this right angle triangle, you can say BA length is nothing but BD into cos of theta minus phi r. Yes or no? Yes, that's the purpose of all these things here. That's the purpose of all these things. Okay, so let me write now. Let me write. Yeah, so let me write in the next slide. That is from right angle triangle, from the right angle triangle, from triangle, you see it is BAD or ABD, whatever it is. BA length is nothing but BD into cos of theta minus phi r. That BD length is IR into Z. And this is cos of theta minus phi r. BA is equals to BD into cos of theta minus phi r. Okay, done. Now you can write from phasor diagram again. OA equals to OB plus BA. As we know, OA length equals to OB plus BA length. And what is that OA length we have? Mod Vs cos of pi s minus phi r. Pi s minus phi r. And OB length is mod Vr. Yes, BA length is IR into Z cos of theta minus phi r. IR into Z cos of theta minus phi r. Like this you can say. Next thing. So I am asking one very simple question to you. Simple question. Who will decide this angle phi s minus phi r? Is it a low angle or high angle? Who is going to decide? Phi s minus phi r angle, who is going to decide? That's the angle between sending end voltage and receiving end voltage. That's okay. Sending end voltage and receiving end voltage, phi s minus phi r. Who is going to decide that? See, you see in this phasor diagram itself, the gap between Vs and Vr, is decided by this length of BD, decided by the length of BD. For example, if this length is very small, obviously these two phasors will come very close, right? These two phasors will come very close, then obviously phi s minus phi r angle will be very low, you can see. That BD length is going to decide that. That BD length is what? IR into Z. BD length is IR into Z. Now, what line we are discussing now? What line we are discussing? Short line. We are discussing about the short transmission line. For the short line, assume that impedance is very less. Series impedance is very less. Then IR into Z value will be very less and BD length is very less. If the BD length is very less, obviously you can say that phi s minus phi r is a low angle and cosine of that low angle is very close to 1. Cosine of that low angle is very close to 1. Okay, let me write. Let me write. For short length of lines, Z is low value. Z is low value. That implies impedance drop magnitude is low. That implies you can say that Vs and Vr phasors will be very close. Vs and Vr phasors, not numbers, phasors are close. That means you can say phi s minus phi r is low angle. That is a low angle for us. Cosine of that angle is approximately equals to 1. Cosine of that angle is approximately equals to 1. Okay, so if you keep that approximately 1, you can say from this, therefore, sending end voltage magnitude will be approximately equals to receiving end voltage magnitude plus mod IR into mod Z into cosine of theta minus phi r, you can say. Mod IR into mod Z into cosine of theta minus phi r. Like this, you can write the sending end voltage magnitude. Mod Vs. And you can get from this mod Vs minus mod Vr quickly. So approximately equals to mod IR into mod Z cos of theta minus phi r. Mod IR into mod Z cos of theta minus phi r. Okay, now you can move with the voltage regulation equation. For short transmission line, particularly we have written voltage regulation like mod Vs minus mod Vr by mod Vr. And it will come like mod IR mod Z cos theta minus phi r by mod Vr. Mod IR into mod Z into cos of theta minus phi r by mod Vr. So from this you can write mod IR mod Z by mod Vr into cos theta minus phi r. Mod IR into mod Z by mod Vr cos of theta minus phi r, like this. Okay, so next I can say here IR into Z is absolute voltage drop. IR into Z is absolute voltage drop. VR, you assume it as rated voltage for time being. For time being, you assume this as rated voltage. So this you can write it as per unit voltage drop into cos of theta minus phi r. Per unit voltage drop is Z drop. Per unit impedance drop into cos of theta minus phi r. Per unit impedance drop into cos of theta minus phi r. Like this, like that you can write. Like that you can see. Okay, next. Let's continue with this IR into Z by mod VR. IR into mod Z by mod VR. Just take up this. Can be rewritten like mod Z by mod VR by mod IR. Look here, please. We can write this one like mod Z by mod VR by mod IR. Assume that these are rated values, or you can say base values for time being. Assume that these are rated values, or you can say base values for time being. So you can write this like mod Z by it is Z base. Mod Z by Z base. VR is V base, IR is I base. So V base by I base, that will be Z base. So this will come to be magnitude of impedance in per unit domain. Magnitude of impedance in per unit domain under rated conditions. Under rated conditions. Okay. So I can write voltage regulation. See, per unit impedance drop what we have now, that you can replace with a Z per unit. That's the thing I'm saying. Per unit impedance drop, you can replace with a Z per unit into cos of theta minus phi r. So you can write per unit voltage regulation is equal to Z per unit into cos theta minus phi. Z per unit into cos of theta minus phi r. And if you want to get the percentage value, you should write percentage Z cos of theta minus phi. Percentage voltage regulation is equals to percentage Z into cos theta minus phi. Cos of theta minus phi. Okay. Percentage Z cos of theta minus phi. So let's move. Let's expand this. Let's expand this one a little bit. So per unit voltage regulation, let me expand. So you can write Z per unit. Okay. So what is the cos of theta minus phi r expansion? Cos theta cos phi r 1 term plus Z per unit into sin theta sin phi r. Sin theta sin phi r. Z per unit cos theta cos phi r plus Z per unit sin theta sin phi r. What do you mean by Z per unit cos theta? Z per unit cos theta is what? Just you look at this impedance triangle. Look at this impedance triangle. What is cos theta? What is cos theta? R by Z. What is sin theta? Sin theta, that will be x by Z. X by Z. And Z cos theta is nothing but R. Z sin theta is nothing but X, you can say. Okay. So you can say here, this is a resistance per unit and this is a reactance in per unit. Resistance per unit and the other one is a reactance in per unit. Yeah, please complete it quickly. I will move to next slide. Once after completion, please raise your hands. So you can say per unit voltage regulation is equal to R per unit into cos phi r plus X per unit into sin phi r. And if you want to get that percentage, you can write percentage R cos phi r plus percentage X into sin phi r. Percentage R cos phi r plus percentage X into sin phi r. Okay, see, actually, all these things, whatever we are discussing now in the form of voltage regulation, all these things we are doing for lagging load. All these things we are doing for lagging load. That's what we have taken earlier, right? The starting itself, we said we have a load of lagging in nature, and for that lagging load only we are doing all these things. For example, if the load is leading in nature, what will happen? If the load is leading in nature, what will happen? Just check here. If it is leading, in place of this minus, you will get plus. In place of this minus, you are going to get plus. And here also you get plus. And cosine of theta plus phi r expansion will give cos theta cos phi r minus sin theta sin phi r. Means here you are going to get the minus. So I will show here. This is plus minus, plus for lagging load, minus for leading load in this equation. Plus for lagging load, minus for leading load in this equation. But whereas in this equation, minus for lagging, plus for leading. Minus for lagging, plus for leading. Okay. So in this equation, I'm going to say plus for lagging and minus for leading. Plus for lagging load, okay, and minus for leading load. Leading. Getting all of you? Percentage R cos phi R plus or minus percentage X into sin phi R. Now, see, voltage regulation value depends upon what factors here? Generally you tell me. Generally, you tell me, please, on what factors this voltage regulation value will be depending. I'll tell you two things. Just by going with the original equation, maybe this one you take and just check here. One is a receiving end current magnitude, definitely. Means load. According to the load variation, definitely voltage regulation is going to be changed. Load variation means two things now. One, it's a current variation. Next one is a power factor angle variation. Because of power factor variation, we have the voltage regulation change. Because of the load current change also, we have the voltage regulation change. So voltage regulation depends upon two quantities or two factors. Voltage regulation depends on two factors. Two factors. Number one, you see this. Number one, load current or load quantity. Load quantity. Because listen, so if the load is getting doubled, obviously we say current is going to be doubled almost. If the load becomes half, current is also becomes half. In that perspective, let me write first. Voltage regulation is proportional to the current magnitude, and that current magnitude will be proportional to quantity of the load. Quantity of the load at a given power factor. At a given power factor or at a constant power factor. This is one thing. Second one is voltage regulation depending upon the power factor angle. Load power factor or load power factor angle. Load power factor, or you can say load power factor angle, means phi r. Right? So these are the two things. Two things you can say. So let me discuss a bit detail about these things. First one, I will say voltage regulation versus load quantity. Voltage regulation versus load quantity. Next one, voltage regulation versus power factor angle. These two things we will discuss, and we will close this so-called short transmission line study by discussing some small problems. Yeah, let's say in the next slide. Voltage regulation versus load quantity. Load quantity. See, it's very simple thing. Already we mentioned that voltage regulation proportional to quantity of load. In that perspective, simple. If the load gets doubled, listen to my words, please. Load gets doubled, current will be doubled, voltage regulation also doubled. Okay. If the load becomes half, current becomes half, voltage regulation also becomes half. Means voltage regulation at n times of full load condition, is equal to voltage regulation at the full load condition, multiply that number n. That n may be 1/2 or 0.6, 0.8, 2, whatever it is. First you calculate voltage regulation at full load condition. And if he's asking at half full load, multiply this 1/2. If he's asking at 3/4 full load, multiply with 3/4. That's so it will be n into voltage regulation at full load condition. This is at a given power factor. You can say this is for constant at a constant power factor. a constant power factor. So I think if you're getting this voltage regulation versus load quantity, but the more important one will be voltage regulation versus power factor angle. Power factor angle is more important for us. Yeah, so I'm saying in the next slide, voltage regulation versus power factor angle. Voltage regulation versus power factor angle. Let's look back to the voltage regulation equation once. Under rated conditions, I am saying you, under rated conditions, voltage regulation equation is percentage Z cos of theta minus phi r. Percentage Z is a constant number into cos of theta minus phi r. Phi r is a variable now in our study. So voltage regulation is equals to percentage Z magnitude cos theta minus phi r. It is at rated conditions. This is at the rated conditions. Or you can call full load condition. Rated condition, or you can say it is full load condition. Full load condition. Yeah. First of all, one small observation what you can make is voltage regulation versus power factor angle, it's a non-linear variation because of cosine. Because of the cosine, it will be a non-linear variation. Okay, see, I'll show these things first. Just observe. This is a power factor angle axis, phi r, and this is a voltage regulation axis for time, whatever it is. Just listen to my words. Else you forget about that voltage regulation and all. Just I am taking the power factor angle axis here, phi r axis. Listen, all of you, stop writing. Just listen to me, what I am saying. Cosine of theta minus phi r, I will construct on this graph. Theta is a constant angle, na? Theta is a constant angle. So cosine of theta minus phi r, we have to construct. First, I will construct cos phi r signal. Cos phi r. So I'll show angles or something like this. Okay. So this is a cos phi r signal I am showing. Observe kindly what I am drawing here. This dotted signal, what I have drawn is cos phi r. Cos phi r. Next one. But I need cos of theta minus phi r, right? Cos of theta minus phi r means this has to be shifted. This curve has to be shifted by an angle of theta. By an angle of theta, this curve has to be shifted. Okay. So I'll show that theta. Before moving to that, let me show this midpoint also. It's also important for us. Theta. Generally, the theta angle will be less than 90 degrees, right? Theta angle will be less than 90 degrees. So I might be showing that angle theta something here. Means this gap what we have is a theta angle. So the same point I should show here also on this one. So in a shift, maybe here you can get it. Okay. So here you may be getting. Okay. Shifted. This curve we have to shift by an angle of theta. By shifting it, you might be getting something like this. Something like this you can get. This cos of phi r minus theta. This is cos of pi r minus theta. Okay, but cos of theta minus pi r is also same thing. Cos of theta minus pi r is also same. Yeah, all of you following this one, please tell me. All of you following this, please tell me. Yeah, good. Next thing, listen, please. See, this blue color curve, what I have brought, blue color curve, I multiply with percentage Z. This blue color curve, I will multiply with percentage Z. That itself is a voltage regulation curve. Yes or no? cos of theta minus phi r curve, what you got now, I will be multiplying that with percentage z. That itself is a voltage regulation curve. Voltage regulation curve. But you see, this phi r angle, I will show here angles on the axis 0 degree, and this will be 90 degree, and this will be 180 degree, and this will be 0. Okay, this is minus 90, this is minus 180. Like this, you have the angles, right? Like that, you have the angles. But you know this phi r, power factor angle, will be in the range of minus 90 to plus 90 only. All of you getting this word? This phi r angle will be only in the range of minus 90 degree to plus 90 degree. Yes or no? Practically speaking. So, whatever this blue color curve portion you have between minus 90 to plus 90, between minus 90 to plus 90, that itself we should consider as voltage regulation curve. Means you should take up only this portion, red color portion, as a voltage regulation curve. Getting me? Only this portion you should consider as voltage regulation. So this is a way how we are going to get the voltage regulation curve in an approximate manner. Approximate manner. Yeah. So I'm going to consider only that portion of curve. I'm going to consider only this portion of curve in the next slide as a voltage regulation versus power factor angle. So I'm saying here, so this is a power factor angle axis, and this is a voltage regulation axis. You have upper side positive voltage regulation, I'll say. Bottom side you have the negative voltage regulation, and this side phi r angle, and this side is also phi r angle, and this side I'll say lag, and this side we are saying lead. Rather than minus 90 plus 90, I'm saying lagging and leading. And you know, this point angle is 0 degree. This point angle is 0 degree. Yeah. So let me tell you. This plot I'm going to take up. This red color plot I'm going to take up. Just observe. I have to show minus 90 plus 90, right? To show that this is 90 degree lagging side or leading side, and this will be 90 degree lagging side, almost lagging side. Now you see that voltage regulation curve will start from this 90 degree at some point here, and then reaches to some peak, comes down. So you may be getting voltage regulation curve. It's a cosine wave shape, of course. Cosine wave shape, of course, like this. Like this, we can experience voltage regulation curve. Yeah, all of you getting this one? So once after completion, I will move to next slide to take up further comments. Actually, the power factor angle will be having a range only between minus 90 to plus 90. Power factor angle, practically, we have a range from minus 90 to plus 90 only. So we no need to take up this whole cosine curve. We no need to take up this whole cosine curve. We have to take only from minus 90 to plus 90. That will be sufficient. That's right. Next thing. You observe. Starting from this 0 degree to 90 degree, lagging side. How is the voltage regulation number all the time? Positive. Always voltage regulation value will be positive for lagging power factor loads. Okay, that's the first comment, right? For lagging loads, always voltage regulation is positive. Lagging loads, always voltage regulation is positive. Is one comment. Next one. How it is for leading loads now? How it is for leading loads? Leading loads. See, if you look at the leading load, some portion we are getting positive voltage regulation, some portion zero, some portion we are getting negative voltage regulation. So for leading loads, voltage regulation might be positive, negative, or it may be zero. All three possibilities you get for leading. So I can say for leading loads, voltage regulation might be either positive or negative, or it may be zero, also, you can say. Voltage regulation might be positive or negative, or it may be zero. All three chances you have. Next, could you please tell me for UPF load how it is? What do you mean by unity power factor load? Power factor angle zero, na? Power factor angle is zero. Of course, I know it is positive. That's clear. It is positive. How much is that value to be expected? And if you keep that phi r is equals to 0 in this, phi r equals 0 in that, you get voltage regulation as percentage Z into cos theta. Percentage Z into cos theta. So voltage regulation will come to be percentage Z into cos theta. What do you mean by that percentage Z into cos theta? Percentage resistance. Percentage Z into cos theta is percentage resistance. So I can say this value was percentage R. That value was percentage R. Next thing. At what condition we are going to get the maximum voltage regulation? At what condition we are going to get the maximum voltage regulation? Which type of load will give the maximum voltage regulation? Which type of load will give the maximum voltage regulation? Only lagging load. Because you see this cosine wave will touch the peak value at only once in the span of 180 degree. In 180 degree angle gap, sine wave or cosine wave will touch to peak value at only one point. That is this, approximately. Okay. And the question is, what is the maximum voltage regulation value and what is the condition for maximum voltage regulation? Can anybody tell me what is maximum voltage regulation? Voltage regulation formula is percentage Z cos of theta minus phi r. What's the maximum value of this one? Percentage Z only, right? Then, whenever cos of theta minus phi r is equals to 1, voltage regulation will be equals to percentage mod Z. That will happen at lagging load here. I'll show it. First, I have to show this is percentage mod Z. I'll show in the next slide. Condition for maximum voltage regulation. Condition for maximum voltage regulation. Maximum voltage regulation. First one occurs at lagging load. Okay, that's one thing. And maximum voltage regulation value is percentage mod Z. We are saying directly. Now the condition is cos of theta minus phi r is equal to 1. Cos of theta minus phi r is equals to 1. Yeah. What do you mean by this cos of theta minus phi r 1? Theta minus phi r is equals to 0 degree. Theta minus phi r is equals to 0 degree. Now the condition is power factor angle equals to impedance angle of transmission line. Whenever power factor angle phi r is equals to impedance angle of transmission line, at that time we are going to get the maximum voltage regulation. Means in this graph, you observe this point angle is theta. This point angle will be theta. Phi r is equals to theta. That's the condition for the maximum voltage regulation. Maximum voltage regulation. Okay. Next, what is the condition for zero voltage regulation? First, it will happen for leading load. It will happen for leading load. I'll show you. Condition for zero voltage regulation. Condition for zero voltage regulation occurs for leading load. Occurs for leading loads. And what is the voltage regulation for leading load? What is the voltage regulation equation for leading load? Anybody? Percentage Z cos theta plus pi r you will get, na? For leading loads, you are going to get that voltage regulation as percentage Z cos of theta plus pi r. And as it is required to make the voltage regulation 0, as voltage regulation value was 0, I should say cos of theta plus pi r is equals to 0. Cos of theta plus pi r equals 0. Then obviously you can say theta plus pi r equals to 90 degrees. And what is the power factor angle? 90 degree minus theta, at which we are going to expect the voltage regulation as 0. Voltage regulation equals 0 occurs for a power factor angle phi r equals to 90 minus theta. 90 minus theta. That you can show in this graph. Okay. So this angle of phi r is 90 degree minus theta. 90 degree minus theta, at which you get the 0 voltage regulation. Now, tell me please, for 90 degree lagging side, 90 degree lagging side, what is voltage regulation? 90 degree lag. And 90 degree leading side, what is the voltage regulation? Tell me please. Tell me please. 90 degree lagging side, how much? 90 degree leading side, how much? I have explained that in Imtiaz earlier. Lagging equation we have derived. Leading equation will be just sign change, right? See, if you, sorry, for lagging side, you keep 90 degree in this equation of lagging side equation. Now, lagging side equation is this, na? You keep 90 degree here. Cos of theta minus 90. So it will be cos 90 minus theta, sin theta. Z sin theta. What do you mean by Z sin theta? X. So it will be percentage X. Percentage X. And 90 degree leading side. 90 degree leading side, if you see, this one, leading equation. If you keep 90 degree here, cos 90 plus theta, that will be minus sin theta. So it will be minus percentage X, you can say. Minus percentage X. So this is a whole thing about the voltage regulation curve and condition for maximum voltage regulation, zero voltage regulation and all we have. So we'll stop at this point today. So tomorrow we have a class from 7 to 1. Tomorrow we have a class from 7 a.m. to 1 p.m. 1 p.m. or up to 1:30 I may take. Okay. 7 a.m. to 1:30 p.m. I will be taking. Yeah. So if you have any doubts, you can ask me. Tomorrow we'll discuss some problems in this short line. We'll be discussing some problems in the short line. And then we will be starting the medium line analysis. Right? If you have anybody having doubts, you can raise your hands now. You can raise your hands now if anybody having doubts. Vishnu.
Sir, my doubt is regarding this transient part, sir.
Transient.
Like yesterday's class, It is mentioned that during this transient, like whenever we connect a load, we generally go for steady state analysis.
No, steady state analysis only we are doing.
Yes, sir. And we consider in steady state analysis only, we'll consider the load.
Yes, correct.
But my doubt is not generally that's only thing, sir. When during transient analysis, suddenly some fault has occurred, that time is also this load is connected.
Okay.
So that time we do not consider the load or
Load might be there, but it may not draw any power at the time, no?
Because the fault is occurring in between.
That depends again whether the load is going to draw the power or not going to draw the power. That depends upon type of fault and where is the location of fault and all.
Okay, sir. And, I think that's all, sir.
Okay, fine.
All right, thank you, sir.
Vishwanath.
Sir, am I audible, sir?
Yeah.
Sir, actually, we are taking the pi model and t model now, sir.
Yeah.
You said that in the pi model, there are no extra nodes, so that's why we are taking the pi model as regarding the t model, there are extra nodes, so that's why the IBS is complicated. But in the pi modes also, there are 2 nodes now, sir. At C by 2
those
and
two are same, no?
Yeah, sir. But the left side C by 2 is referred to VS and the right side one is referred to.
If you want, you move that C by 2 to the node where you are taking.
Sir?
Move that C by 2 to the node where you are taking.
Yeah, sir. Then there are 2 nodes occurring now, sir. If the C by 2 is moved to the
resultant nodes will be 2 only, right?
Yeah, sir.
Then?
Yeah, okay, sir. And sir, we are taking the
if you have zero impedance between any 2 nodes, will you consider that as a single node or 2 nodes?
Okay, sir.
Okay?
Yes.
Yeah.
Sir, and the capacitor is taking into the admittance now, sir. Why not impedance?
No, that's just for the flexibility in the analysis, I said. If you want, you can take the shunt element also in the impedance form, no issue.
Yeah, okay, sir.
But there you have to do the analysis like series impedance Z1, shunt impedance Z2.
Sir, coming in, I don't understand.
Series impedance, you should say Z1.
Yeah.
Shunt impedance, you should consider Z2.
Then the problem is getting complex.
Not complex in the sense, in the way of understanding, it is a bit difficult. That's the thing.
Yeah, okay, sir.
Okay.
Sir, and in the ABCD parameters, for A equal to D, you said the symmetric. It is the symmetric.
No. Actually, for symmetrical networks, A equals to D will occur.
Yeah, okay, sir.
From examination point of view, to check whether the network is symmetrical or unsymmetrical, we used to check whether that A equals to D or not. But what is the original statement? For symmetrical networks, A and D are equal.
Okay, sir.
That's the meaning. Okay.
Sir, are there any other definitions for passive networks?
Actually, if the network is satisfying the reciprocity theorem, then that network is going to be called as passive network.
Okay, sir.
Reciprocity theorem in the sense, response to excitation ratio remains same, even though response and excitations are interchanged.
Okay, sir.
For example, we keep a source at one point, we measure voltage or current at some other point in the network. Okay?
Sir? Okay, sir.
You are keeping source at one point. Let's say voltage source at one point. You are measuring current at some other point in the network.
Yes, sir.
And that response is current. Voltage is an excitation.
Okay, sir.
So response to excitation ratio, that current to voltage ratio you calculate. Next time, you interchange these two. You move your excitation to response location, response to excitation location.
Okay, sir.
Then you do the calculation. Again, you calculate response to excitation ratio. If it is coming same, then the network is reciprocal.
Okay, sir.
For a pure impedance network, it will happen, definitely.
Yes, sir.
If you don't have any other source in the network, then definitely network will be passive.
Okay, sir.
Yeah.
Thank you, sir.
Yeah. Navdeep.
Sir.
Tell me, Navdeep.
Sir, I am not understanding what is charging current, sir.
Charging current yesterday also I have explained, right?
Sir, once repeat, sir.
Have you attended doubt session yesterday?
No, sir. I left at the end only.
See, these are the two lines we have, let us say. So it's a line A and you say it's a line B, operating at different voltages.
Yes, sir.
I'll say this is having a charge of Q. Line A is having a charge of Q. And it will be having electric flux lines radially outward, right?
Yes, sir.
Okay, whatever the electric flux lines leaving from A, it will be touched B.
Yes, sir.
Right? So the conductor B is experiencing electric flux lines because of A.
Yes, sir.
Okay. But this operating voltage of conductor A is a sinusoidal one.
Yes, sir. Yes, sir.
And obviously charge is also sinusoidal.
Yes, sir.
This flux is also sinusoidal.
Yes, sir.
Whenever the sinusoidal flux links with this conductor B, this conductor B experiences a rate of change of electric flux.
Yes, sir.
What do you mean by rate of change of electric flux?
Current will induce, sir, in it.
That's the charging current.
Okay.
So current is induced in the conductor B because of conductor A electric flux. Or because of the potential gap between these two, there is some current got induced in the conductor B. That's what we are naming as charging current.
Sir, in case of transmission.
Listen. Is it required to show this in the circuit or not? Whatever the
No.
charging current you are saying, getting induced in the B due to A, is it
Yes,
required to show in the circuit or not?
Yes, sir.
Yes. That's why we are keeping a capacitor to say that there is a charging current.
Okay,
See, if that current is getting induced in this one, who is supplying that current indirectly?
Conductor A.
Conductor A.
Okay, sir.
Okay.
Understood.
Tell me, what's your doubt?
Now understood, sir. Now another doubt, sir. In voltage regulation, sir. Sir, how it converted into per unit? Then we have to divide by base unit, base of voltage, sir.
Just per unit in the sense cancellation of units. That's it. Right now. It's not that per unit value, taking base value and dividing that. That's not that. Just it's a voltage to voltage ratio, right?
Sir, but here you have converted that voltage regulation into per unit voltage regulation, sir.
By choosing that we are approximately base, you say, if you want that statement. That receiving and voltage magnitude mod VR you have not?
Yes, sir.
Under rated conditions, you assume that as close to the rated voltage, so that itself is going to act as a base.
बट जो वोल्टेज रेगुलेशन की वैल्यू हम निकालते हैं उसको बाद में बेस से डिवाइड करते हैं ना सर उसको
तो जब we don't divide that voltage regulation again with the base.
सर फिर ये पर यूनिट में कैसे कन्वर्ट होगा ऐसे पर यूनिट में तो
per unit value
actual value by base value.
Okay, so actual value we have taken mod vs minus mod vr approximately.
Yes, sir.
Base value mod vr.
Yes, sir.
Divided. That's a per unit.
Okay, sir.
Okay. Then how you divide that voltage regulation again with the base? Voltage regulation already don't have any units, right?
Yes, sir. Yes, sir.
As already voltage regulation is not having any units, dividing that with the base is meaningless, right?
Okay, sir.
Any other doubt you have, Navdeep?
No, sir. Thank you, sir.
Okay. Avinash.
Hello, sir.
Tell me, Avinash.
Sir, I have not got the voltage regulation curve, sir. That how it comes, sir? Actually.
I explain, no. Cosine curve.
Yes, sir.
First, I have drawn the cos phi r curve. Black
yes,
color. Cos phi r. Have you understood cos phi r?
Yes, sir. Yes, sir.
Then I need cos of theta minus phi r.
Yes, sir.
So I shifted this black curve by an angle of theta.
Okay, sir.
So this is a blue color curve I got by shifting that by an angle of theta.
Yes, sir.
So that is cos of pi r minus theta. Else you say cos of theta minus pi r also.
Okay, sir.
So I got this curve, right?
Yes, sir.
If I multiply that with percentage Z, you will get voltage regulation.
Okay, sir.
So this peak value will become percentage Z. That's it.
Yes, sir.
Curve will be remains, curve looks to be as it is. Numbers might be changing. That's it on the curve. Position will be same for the curve.
Okay, sir.
But you know, power factor angle will have a range only between -90 to +90.
Yes, sir, Maharaj.
That's why I'm taking only from -90 to +90. Whatever the portion of this blue curve we have, that's the voltage regulation curve.
Okay, sir.
Okay?
Yes, sir. Yes. Thank you, sir.
Yeah. Bala Viknesh.
Sir, I have a general doubt, sir.
Yeah.
Sir, in impedance triangle, there will be an angle called theta, sir.
Yeah.
By that theta, can we find the power factor, sir?
No.
Oh, okay, sir. It's only the angle for finding the impedance, like R by Z, like that, sir.
That is the impedance angle of transmission line.
Okay, sir.
What is power factor?
It's a power factor means phase difference between voltage and currents.
Who will decide that phase difference between voltage and current?
Hello, sir.
Who will decide the phase difference between voltage and current?
The supply from supply, what we get under impedances, sir.
Which impedances?
Reactance and I mean capacitive reactance, inductive reactance.
Tell it again, please. Cosine of angle between voltage and current, you said.
Yes, sir.
Who will decide this current value? Voltage value, let's say source.
Yes, sir.
Voltage value, let's say source. Who will decide current value? In the
Load,
line?
based on the load.
Yes.
Okay,
Understood
sir.
now?
Yes, sir.
Power factor means what? Cosine of angle between voltage and current. That's okay.
Okay, sir.
But current is not going to be decided by your line impedance. It is decided by your load.
Okay, okay, sir.
Okay?
Yes, sir.
Yeah. Any other
Sir,
doubt you have? Tell me.
What is in the reciprocal network, sir? You said reciprocal network and
Just now I
symmetric.
explained, right? Passive network. I explained.
Can you please once
Network,
again?
network does not have any sources, you can say.
Okay, sir.
Network satisfying reciprocity theorem.
Okay, okay, sir.
And means the response to excitation ratio remains same, even though response and excitations are interchanged.
Okay, sir.
If the network is consisting only passive elements, there is no active element.
Then it is called reciprocal networks.
Reciprocal network. Yes.
That's it. Thank you, sir.
Yeah. Haripriya.
Good morning, sir.
Yeah, tell me. Haripriya.
Sir, what are maximum voltage regulation and zero voltage regulation?
See, just we are checking at what load power factor angle we are going to get maximum regulation. At what load power factor angle we are going to get the zero voltage regulation. That's it.
Sir, maximum voltage regulation means, shall we say, like maximum rise in the receiving end voltage, like that?
No. Maximum rise in the
Receiving end voltage.
okay, you can take it by removing a load.
Okay, sir. I mean, what that the term means exactly, maximum voltage regulation. What does it tell?
Maximum voltage regulation is going to indicate obviously voltage drop, maximum voltage drop, approximately, not exact meaning. Approximately, you can say maximum voltage drop.
It's maximum rise, we can say, sir.
Maximum rise in the receiving end voltage when the load is getting disconnected.
Okay. Zero voltage regulation means, sir, there is no change.
There is no change in the voltage.
Thank you, sir.
Okay. Naveen Sai.
Sir, my doubt is from first chapter, sir. There is a question. I mean, you also explained about selection of conductor based on for less than 220 kV, it is on current rating. For greater than 220 kV, it is based on corona. That means
Okay.
flux. But in material, there is a question, sir. It is given 220 kV, and the answer is again corona, sir. I mean,
no, it's not corona. You modify it.
Okay, sir.
Okay.
And one more, sir. There is a statement like this, sir. In the whole power system network, we can find neutral wire only in secondary
distribution.
That means the transmission lines are connected in delta. Can we conclude in
No.
this way, sir?
How you can say that conclusion? What is
I
the connection
mean,
of transmission line, Naveen? I think you have attended FNS also.
Yes, sir.
What is the meaning of delta? Just we are seeing 3 wires there.
Yes, sir.
If you don't have neutral, you should not say it is delta, right?
I mean, in delta there is no neutral, no, sir. Again,
Star ungrounded also no neutral. Star
okay.
grounded also no neutral.
Okay, sir.
You should not say the transmission lines are in delta or star anywhere.
Okay, sir. And
You should not say that statement first. You have 3 wires, that's it.
Okay, sir. And one more thing, sir. And I mean, there is I mean, I searched in some books, sir. They are saying if transmission lines are connected in delta, it is more economical. Is it so, sir?
It's a completely wrong statement. You send me in which book it is?
I mean, generally I searched in net, sir.
The internet, why you are searching for it? Already have some standard textbooks.
Okay, sir. Okay.
Don't confuse with the internet. Don't confuse with the internet. Better if you are having that much amount of time to have a search in the internet, better you see a textbook. That is better.
Okay, sir. Okay.
Don't say transmission lines are in delta or star. Just those are 3 wires.
Okay, sir.
In case of windings only, you will say it is star or delta.
Okay. I mean, depending on our requirement, we modify the connection, sir. No.
Again, you are saying connection.
I mean configuration. Star ungrounded or again.
See, star grounded or star ungrounded, that will be decided by your nearby winding.
Okay.
Is it a generator nearby to that or transformer nearby to that? That winding neutral, if it is grounded, I will say it's a 3 line, but neutral is provided by ground.
Okay, sir.
There also 3 phase 4 wire.
Yes, sir.
But 4th wire we are not running. It is taken as ground.
Okay, sir.
But in case of secondary distribution, especially we are running the neutral wire.
Okay, for load purposes. Okay.
Yeah, don't practice questions from internet or some other thing. If you have time, better you go with previous gate questions. Have you done all previous gate questions?
From our material, I completed the practice.
I'm asking you, have you done previous gate questions, previous IES questions, previous civil services questions?
No, not completely, sir.
That you do first, rather than going questions in internet.
Okay, sir.
Because internet questions are framed by some people, who may not have a holistic idea about the subject.
Okay, sir.
I'm not criticizing them, but still.
Okay, sir. I understand.
Okay. So, but gate questions, IES questions are created by the people who is having holistic idea.
Yes, sir.
Please practice those questions. That will be better. Okay.
Thank you. Okay, sir.
Yeah. Shiva.
Sir, I have a doubt in voltage regulation.
Tell me.
Final equation. The percentage R cos phi plus percentage.
Okay. What's the doubt?
The percentage R, can we use it as the percentage resistance drop, sir?
Percentage resistance only. Percentage resistance drop you want to use. You can use it.
Yes, sir. And then in previous like 55 years. Sir.
Okay.
Sir, how you got the percentage X and 90% X? Could you explain?
No, in case of lagging side, what's the voltage regulation formula? Percentage Z cos of theta minus phi r.
Yes, sir.
If you keep phi r equals to 90 degree, so you get cos of theta minus 90.
Yes, sir.
Then it is cos 90 minus theta. So sin theta, Z sin theta, percentage X.
Okay, like theta we are assuming.
Whereas you can say in case of leading side, it is percentage Z cos of theta plus phi r.
Yes, sir.
And if keep phi r equals to 90, cos 90 plus theta, it will be minus sin theta.
Okay, sir.
So it will be minus percentage X for 90 degree leading side.
Yes, sir.
Okay?
Okay, sir. Thank you.
Any other doubt here?
No, sir. No, sir. That's it.
Yeah. So if anybody have doubts, please raise your hands. Else we will close this session. Yeah, Avinash, tell me, Avinash.
Sir, in a primary distribution system, sir, whether neutral is required or not, sir? Actually.
Primary distribution?
Yes, sir.
That depends upon their requirement actually. If you are giving directly 11 kV supply and if they have their own transformer, you don't need to supply the neutral.
Okay, sir. Means it is not necessary, sir.
Not necessary. You no need to supply the neutral. The consumer, what you have, they will create their own. For example, you see in the apartments.
Yes, sir. Means where the
Apartments, they will give only 3 wires as the input. As a distribution company, they will give only 3 wires input.
Okay, sir. Means neutral is
Neutral wire is taken from ground.
Okay.
Okay.
Yes, sir.
Yeah.
Thank you, sir.
Yeah. Here, Babu. Here, Babu. So I'm closing the session. Thank you. I think nobody's having a doubt. Pavan. Pavan, do you have any doubt, Pavan? Pavan. So I'm unable to listen to you, Pavan. Balashankar.
Hello.
Tell me, Balashankar.
Sir, leading and lagging concept क्या है?
Current is in leading with respect to voltage. That's the meaning of leading.
Current
is leading with respect to voltage because of the capacitive load.
Okay, sir.
So current is lagging with respect to voltage because of inductive load.
Okay, sir. Thank you.
Okay. Yeah. Anybody have doubts? Raise your hand. Else we'll close. Okay. Thank you.